Thank you. Okay, welcome back to the hydrodynamics lectures, and this is our first lectures. So yesterday I gave you the basic equation for the relativistic hydrodynamics in curved space-time initially, and then so I jumped into the special relativistic hydrodynamics and how to solve this Riemann problem in 1D to get the exact solution for the Riemann solver. So today, the main topic is the numerical, the scheme or approximate Riemann solver to solve the relativistic hydrodynamics and relativistic magnetohydrodynamics. But before jumping to these topics, I want to introduce the part I skipped yesterday, or namely the basic equation for the electromagnetic hydrodynamics in curved spacetime. 3+ on the composition of the electromagnetic hydrodynamics, right? So let me recap the basic equation for the relativistic hydrodynamics and the magnetohydrodynamics derived yesterday. So in these forms, I don't assume that any particular form the energy momentum tensor. But if you define the conserved mass D, which is given by the rest mass density rho times the Lorentz factor, and conserve the momentum SI, upper SI, and the energy SL, so you can write down the equation of motion for the relativistic fluid by the divergence T mu nu condition, right? Something like this. So the important point is we define the 3 velocity Di by 4 velocity ui divided by the ut by using the normalization the condition for the u mu minus 1. You can derive these equations. This is a very particular useful quantities. So yesterday I assumed that T mu nu is a hydrodynamic case. Then I derived the equation motion, Euler equations, and energy equation for relativistic hydrodynamics. Today, I will go to the step one more further for the electromagnetic hydrodynamics. Okay, let's start by introducing the electric field and the magnetic field, which is projected on the hypersurface of the 3+ on the composition. So because of this, the upper EA and BR is a vector projected on the hypersurface, it should be the contraction. If you contract with NA, normal vector, in 3+1 hypersurface, it should be 0. Also, BA, NA should be 0, which means that the FAB Faraday tensor could be like in terms of the upper EA and upper BC plus NA, something like this. So by this condition, EA is given by these equations, and the magnetic field is given by these equations, right? So I think that Thomas already mentioned about the Faraday tensor, the Maxwell equations, and he introduced the charge current in this form. And in a 3+1 language, rho E is the charge. Is given by the contraction with JA current, full current NA, plus JA bar is a spatial component of the charged current. Okay, now is the timing to assume the stress energies for the electromagnetic hydrodynamics. And stress energy of TAB is decomposed into the hydro part, which we mentioned yesterday, and plus electromagnetic part. Hydro part is written something like this, and electromagnetic part is something like is written by the Faraday tensor FAB, something like this. If you plug this expression here to this one, after lengthy calculations, you finally get the TAB of the electromagnetic EM field should be written by something like this. Also, you can define the Hodge-Dier so that FAB by this definition, it's going to be reduced to this expression. This is useful for the Maxwell equations. I will show later on. Okay, now is our conserved momentum and energies becomes something like this, and because the rho H is is a contraction of the NA and B, right? And the hydro part we derived yesterday. The EM part here is just contractions in here by NA and B, and the first term is disappeared. Okay, and no, not disappears. So anyway, if you contract NA and B these equations, you get these terms, right? Also, JA definition of JA is the if you contract gamma C and NB, you can also derive this part. This part from this definition, right? And Sij, so the SAB is same. SAB equals gamma AC, gamma BD, DC, yeah, the stress energy tensor CD component. And then so you get these expressions right here. Okay, now so wait. Where is sorry, something. Okay. Now so let's derive the MHD Euler equations by using these relations and that relations. And we only consider the flux terms because the other term is exactly same for this one. Okay, let's do this. Before that, I want to. Yes. Then so.
Why do we not use the Maxwell's equation in curved spacetime?
Oh, I will use Maxwell equations later on. But here's a equation for the fluid part. To evolve the electric field and the magnetic field, we need Maxwell equations. I will write down the Maxwell equation later on. But this is a fluid part because, okay, I will explain more. So total divergence term, divergence mu should be exactly zero, right? This is come from the Bianca identity. And now so we split T mu nu is the hydro part plus EM part. So now sir, I want to derive the hydro part equations by using these relations. by using the Maxwell equation in the curved space-time, this term is going to be the Lorentz force, right? Then so to get the evolution for the electromagnetic field, and this describe the evolution of the densities, momentum, and energies. But we need evolution for the electromagnetic field and the magnetic field. The Maxwell equation so describes the evolution of the electromagnetic field and the magnetic field, something like this. This comes from the Maxwell equation. I will mention later.
But this is the Maxwell equation in flat spacetime.
No. This is a completely general because you have a BI, right? Beta is a shift vector. This is a curved space. Yeah, just I started from the general form of the Maxwell Maxwell equation given like this. Okay, this covariant derivative is contains the information of the curved space.
But I thought Maxwell equation in curved spacetime had a Ricci tensor with coupling with one of the Faraday tensor or
No. The Maxwell stress tensor in general form is given by this form.
So the curved spacetime thing comes only from the covariant derivative.
Sorry.
The curved spacetime information comes only from the covariant derivative.
It's covariant derivative. Sorry. Delta alpha. This is a covariant derivative in 4 dimensions.
So that's where the betas come from.
Huh?
That's where the betas come from. The shift vector.
Shift vector comes from the 3+1 decomposition. Okay. This is a Maxwell's equation. FAB, sorry, FAB. I always mix up. B. Okay. Then, so if you calculate the left-hand side, minus Z delta mu. Sorry, it's A. FAB plus FAC BCD. Something wrong. B. But yeah. Forgot the. Sorry, I did some mix up. C, B, C, A. Yes, right. And because Maxwell stress, Faraday tensor is an anti-symmetric tensor, and this is the symmetric in terms of the AC. This term is a cancel, right? Because symmetric and anti-symmetric, right? And then so this gives you the alpha root gamma over D, alpha root gamma D A B. Right? Then so okay, here is a plus. This is a Maxwell equation. And if you plug this expression, FIB is what's the form of the FIB? Here. IB means NYEB or NBEI, right? And Ni, what's the form of the Ni? Do you remember? And mu is 1 over alpha minus beta I over alpha. So the spatial component N mu contains the information of the shift vectors. Okay. It's okay. Okay. Okay, anyway, so by using these equations, you can derive the Maxwell equations from here. And also for the projection in terms of Na, you get their charge, the Gauss law incurrence instead. And you can do a similar as exactly the same thing for this the Faraday the Maxwell equation, or with the Hodge dual this equations. Then so you get the monopole condition, divergence B equal to 0 here, and the induction equations which describe the evolution of the magnetic field. Okay, this is Maxwell equations. Okay, let's go back to the momentum and momentum flux and energy flux. So here's the expression for the momentum flux in general. So if you plug this expression to here, alpha, gamma, again, so you have to take the careful for rise and down for the velocity of the velocity of the U, because U is a four-dimensional tensor. You cannot raise and down the indices with gamma GL. You need to do it with a G mu nu. The point is like this bird with 3 velocity VI, because the UT as VI, and here becomes the beta J plus shift term times UT by this equation, right? Then so by plugging the low H, alpha times UT becomes a Lorentz factor omega, and beta J plus like this. Then so the final task is to rewrite this part for SI here. Sorry, here. So these terms comes the S I minus 1 over pi so now the shift term for the SI here is cancel out. Yeah, cancel out. Something wrong? No. Then so, okay, finally you get the expression for these flux terms. Okay. And for the energy flux term, it's exactly the same. Okay. Minus S0 beta J plus alpha Sj is the minus S0 beta J plus alpha here gamma low H omega. Again, so here is beta J plus Bj plus beta J times UT. Then, sir, like this. So final task is to rewrite this part, this part as with the S0 or OH. And it gives you the root comma. Like this. And so S0 times the shift of beta J here is cancel out, right? Here and this one and this one cancel out. And so the final expression becomes this one, right? This is the momentum energy flux on a pressure, total pressures, including the EM part, plus contribution from the EM contribution. So this is MHD-Euler equations, which describe the evolution for the momentum and energies. And also, so in this system, so because we write down in a conservative forms, we need a primitive recovery, which means that we have to determine the low omega, low Lorentz factor, rest mass densities, and specific entropy from the conservative quantities. So to do that, the Lorentz factors equation for the Lorentz factor is useful, which is given by the conserved quantities completely. So I have already explained how to derive the Maxwell equation in here, and the final part is the current conservation, and here and generalized Ohm's law, which gives you a closure relation between the electric field of E and magnetic field of B. So in a fluidless frame, the Ohm's laws is given by the current in the fluid frame and conductivity is sigma c and electric field in the fluid frame. So in inertial frame, this the equation is reduced to this one, and this gives you the electric field measured in a fluid frame, not on the normal frame. On the left-hand side is a current. Okay, then so with this generalized Ohm law and current conservation, the system is now closed form. This is a basic for the electromagnetic hydrodynamics. So generalized Ohm's law is furthermore is reduced to be this form. And okay, I have a time. I will derive this expression.
I had a quick question.
Yep.
Does the Ohm's law hold when the fluid is in a state of shock?
Hmm?
Does the Ohm's law hold when the fluid is in a state of shock?
Yes.
Okay.
Let's start from this form. And JA is decomposed into the charge plus spatial component of for current in 3+1 language. So by multiplying the NA, normal vectors, this gives you the minus rho E minus omega. Now Faraday tensor is written as the like this. If you practice express, if you contract the NA and the distance, it gives here, right? Also, by projecting in the hypersurface, this here gives J bar I plus okay. So now we can eliminate the JB UB contraction by the both equation, and it gives the equation for the spatial component of the for current. Okay. by eliminating this expression both. And so finally, J bar I is beta. So now we can express the partial component of the current with the charge and the electric field, magnetic field, and the conductivities. So now we know that the expression for here by these equations, the Ohm's law becomes generalized, or Ohm's law is something like this, right? This is just expression over here. So now you know how to evolve the law E, which has a constraint for the Gauss law. Now you know how to evolve the EI and the electric field and magnetic field. Then the system is closed. But of course, you need to assume that some functional form or the physically motivated model for the conductivity sigma C, of course. But it depends on the situation you want to consider. Okay, this is MHD Euler equations in general form. And if you assume you can reduce furthermore to a simplified system by assuming the infinite conductivity, in which which is varied for the large number of the electron number density E. In astrophysical situations, and this approximation is relatively reasonable. So in this case, we call the ideal magnetohydrodynamics case, because the Ohm's law here is described by the electric field measured in the fluidless frame and current measured in the fluidless frame. If the omega sigma C is infinities, to get the finite value of the current measured in the fluid frame, and electric field in fluid frame should be zero, right? This is the ideal MHD equations. So fluid frame, the electric field in fluid frame is given by the contraction of the Faraday tensor FAB and UV. In this limit, this quantity should be equal to 0 by the Ohm's laws. Otherwise, the current in a fluidless frame diverges. It doesn't have physical meaning anymore. Because we know FAB also written in terms of the upper EA and the upper EB, which is measured in the hypersurface. So now you can derive the relation between the electric field upper EI and the upper BK, something like this, by equating this one. And if you plug the FAB expression here to this here, you get these relations. So the meaning of from these equations, you can immediately arrive the conclusion in ideal MHD case, the electric field should be perpendicular to the perpendicular to the electron field. Sorry. Sorry. The electric field should be parallel to the magnetic field. Then by plugging this expression to, these equations, Maxwell equation. So you can arrive to that induction equation in the very simplified form. This gives you the minus rotation E, and also the monopole free divergence free condition. So the other equation for the electromagnetic field and charge current that gives you the determine the electric field and charge density. So this is not necessary to these quantities are not the dynamical, but not its dynamical value, but we don't have to evolve the electric field and the charge current, and because this system is close to the BI itself, and electric field is given by these equations. And these equations are just giving you the distribution of the electric field and the charge current after you determine the solution from these equations. This is a structure for the ideal MHD case. So in ideal MHD case, Faraday tensor also might be written in this form, because the electric field measured in fluid frame should be 0, which means that the FAB is somehow the proportional to U plus lower BC, where lower BC is a magnetic field measured in a fluidless frame, which is different from the upper B. And also the Faraday, the Hodge dual of the Faraday tensor is written by this. Sorry, this is not parenthesis. This minus BAUA minus BBUA, and which gives you that the magnetic field contraction with UA equal to 0. Then, so the electromagnetic the tensor, the stress energy tensor for EM field is reduced to be here, something like this. And the conserved energies and conserved momentum and SAB is, is given as usual by, for example, this. Right. And now, so you come up with, these terms, B square and B square in the fluid, B square and B square. So that, for example, the B in pressure, B square over 8 pi gives you the magnetic pressures, and also B square in 4 pi in this part is inertia coming from the magnetic field. And also for relativistic collections, you have residual, not residual, but you have an additional term, which is alpha BT, which is proportional to the alpha BT. Also in the current, you have the inertia and also the alpha BT term and blah, blah, blah. So now, we need to derive the relation between the lower BA and upper BA, which is immediately given derived from this relation, and FAB is this relation. This relation, and FAB is this relations. And now, so BA, lower BA is given by this equation, and B square is also given by upper B and the Lorentz factors omega. So I won't repeat this almost the same procedure to derive the momentum equations and energy momentum flux and energy flux, but the structure is similar to generalize the case here, right? These terms becomes this term becomes the pressures, total pressures, including the magnetic pressures. And this system, this form is similar to the ideal MHD in non-relativistic fluid dynamics. Okay, and conserve the momentum and energies. I have already written this one. Oh yeah, sorry, I have already written this one. Please ignore this slide. The final task is the primitive recovery in MHD, ideal MHD case. This is a bit confused, a bit complicated. So yesterday, I derived how to solve how to determine the specific entropy and Lorentz factor in hydrodynamics case with a particular gamma rotational state. And for MHD case, ideal MHD case, the procedure is similar, but this calculation is going to be a bit complicated. So I will derive this one. This is a Lorentz factors equations, and the most important ingredient to derive this expression is a contraction of the momentum SI and magnetic field BI. Now is SI is this expression. So I use an abbreviation like this, right? Then so BU term here and here cancel out this expression. Really? No, sorry, I'm wrong. And BU expression here is cancel out, right? By constructing these terms and these terms. Oh, sorry, B square is just BI. BU. This expression is important. So let's calculate the S square, which is given by the S gamma ij contraction in with SASJ, normalized by the conserved mass. And give me a second. Okay, by using this relation, SI is written by DHI. I just practice BU expression to here. Then so by using the these relations, and this S square becomes gamma A like this. And then so if you expand this expression, for example, first terms gives you the Lorentz factors, right? Because the contraction of the UI uj times gamma j. And then, so it's gonna be sorry. Like this. So the final task is so now, so you have here UIBA constructions and where, and here as well. UIBA construction. So then, so this part is written by the BU construction is related to the SIBA constructions. So then, so after manipulation, after calculating this, S square is finally comes the omega minus 1 H plus B square okay. So this is an expression which describes the specific entropy and the Lorentz factors. This expression is equivalent to this expression. The point in here is a Lorentz factor unknown quantity omega is written by the unknown quantity h times omega plus known quantity. Here's a b square, s square, and the other term is here, and here is just calculated from the conserved quantities, which should be able to that should be able by the Euler MHD equations and the Maxwell equation as well, right? And also, sorry, S square is a contraction of the SI. So we know the SI, D, and B already. So these quantities are known quantities. And if you plug this number, you can find the relation between the Lorentz factors and H omega. Also, the energy density of this zero is written by this one, like this. So we don't know the value of the H omega and pressures, which depend on the equation of state you assume. And then by assuming the equation of state, you can close this relation, because this equation should be regarded as the relation between the omega square and H omega. And this equation also gives you the relation between the H omega and omega square, right? So for the gamma rho equation of state, these terms, pressure divided by the conserved mass, is given by this equation. It's a relatively easy form, which is the H omega, omega square, and omega. So you can solve these equations and these three set equations, not two equations, by like the Newton-Raphson also. This is a way for the primitive recovery for the gamma rho equation of state. Of course, if you assume the different equation of state, like a more complicated one or a tabulated equation of state, you need to do iterative things by Newton-Raphson. Then, so finally, you get Lorentz factor omega and specific entropy H. Then, so you now recover from all the primitive recovery from the conserved quantities. This is a primitive recovery for the ideal MHD case. Okay, this is a basic equation for the relativistic magnetohydrodynamics. Do you have a question, or if you don't, so let's move on to the second part. Okay, so the second part is a high resolution shock capturing scheme for relativistic hydrodynamics and relative magnetohydrodynamics in the curved space term first. So let's derive the finite volume method. Okay, let's define a finite volume method in a curved space time, because our primary target is hydrodynamics, magnetohydrodynamics in a curved space times. So let's consider this is a basic equation for ideal MHD case. The conservative quantity is the density, momentum, energy, plus magnetic field. But this magnetic field should satisfy the dipole magnetic monopole-free conditions, right? And you have a source terms which depend on the curved space-time quantity, like the Laplace function or the shift function. Anyway, let's consider a four-dimensional manifold M, and upper sigma is a part of the manifold M, and how do you say? I don't know how to pronounce it. Anyway, this one omega gives a closed three-dimensional surface. Schematically, so you can write this equation. Omega is part of the four-dimensional manifold, and this one it gives the surface terms for the 3+1 language. Here is a hypersurface at the t or t, and here is a t plus delta t. And here gives the surface in the space. So the time-like surface here, sigma x, for example, in the x directions, should be considered as a time series of the constant tx surface, namely sxt. So let's start from the conservative equation for the T mu divergence. Sorry. Let's start from the energy tensor, divergence of the energy stress tensor. Okay, and if you integrate these equations inside this manifold, you have these equations. By using the Gauss cell, and first time is just the integration in terms of the time t, and the second terms you can use a Gauss theorem for the divergence flux, and then you can write down something like this, right? And you also have a source terms. So let's introduce the proper volume average conserved quantities divided by the QA bar, upper QA bar, which is defined by the integral of this form divided by the three-dimensional proper volume like this. And then so let's consider a numerical cell. And so in finite volume, the numerical cell is an important, the ingredient. So you have a Cartesian cell, and at the centers you have a QEver, and you have the surface, the interface surface terms. So numerical flux through, for example, x directions in here is given by that integration from Tn to Tn plus 1. Tn plus 1 is a T plus delta T, and through that flux at the interface, right? By using this numerical flux, this the equations is reduced to something like this, where the delta AX, YZ is a three-dimensional proper surface of this surface, right? For deriving this equation, we implicitly assume that change in the square root gamma is during the time step is small. Gamma is a proper volume of the three-dimensional space-time. So which means that the proper volume doesn't change significantly during the one-time space. This is not so strong the constraint because in our simulation the delta t or time step is is limited by the speed of light. So in just one time step, this quantity does not change significantly anyway. So now we have these terms. And by introducing the three-dimensional, the determined proper volume or proper volume average or the surface average of the three-dimensional metric determinant gamma j, by using this, and then finally we get the final expression for the numerical magnetohydrodynamics. Also, for the magnetic field, and we have to evolve the magnetic field in this system. And there are a couple of the techniques to evolve the magnetic field. But the most important thing is that magnetic field should satisfy the divergence-free condition. Otherwise, you can get the unphysical solution. In my knowledge, the best way or the best scheme to preserve the divergence-free condition is a constraint transport scheme, in which first you define the magnetic field, for example, Bx in here, cell surface in the x directions, and y and z in the ds directions. And then also you define the electric field. For example, in x direction, electric field is defined on the cell edge. Y is here, the y component is here, and z component is here. By defining the electric field and magnetic field in this location, you can easily calculate the divergence-free condition is satisfied numerically by using the induction equation, because the Vx is evolved by the rotation of this direction, and By is rotation E this direction, and Bc as well. So if the initial magnetic field satisfy the magnetic field the divergence-free condition, and even after update the magnetic field through the induction equation, these the electric field cancel out each other. Then so the next the magnetic field in the next time step also satisfy the divergence-free condition. It is guaranteed in the mass simplification. And let's apply this method. And then so we have to derive the discrete form for the induction equations. So to do that, let's start from by integrating for example, the component of the induction equation on the surface of ds omega. ds omega is part of this surface. And then so the second term, you can rewrite the second term by the Stokes theorem because it contains a rotation of the E. Then so this equation is reduced to this one, right? Similarly, the x component or the y component of magnetic field is given by these equations, where I assume that the surface average the magnetic field in xy direction by xy component by these equations. So numerical flux, it says that the electric field is nothing but the numerical flux. So numerical flux at the edge is given by these equations, and the induction becomes reduced to these equations. It's a bit messy, where delta L is the delta Lxy is a three-dimensional proper length in x, y, and z direction at the cell edge. And if you introduce the proper three-dimensional determinant via the proper lengths x, y, and z, then so finally induction equation becomes something like this. It's a bit messy expression. Now, so we have a discretized form for the conserved quantities at the cell center here. Also, the magnetic field evolution at the cell surface, which satisfy the divergence-free conditions. Okay. So now, so we jump into the how to evaluate the numerical flux, like F tilde x, F tilde, this is a numerical flux, and E tilde x, y, z as well. So there are a couple of the option to evaluate the numerical flux at the cell interface and cell edge as well. So I'm going to explain a couple of them. So broadly speaking, there are two classes for the approximate Riemann solver in general relativities. The one is this is my favorite one. I use because Riemann solver is normally invented in the special relativistic case. So if you go to the curved spacetime, you need to reformulate in a curved steps again, but sometimes it's going to be messy. So the most smart way is by using the tetrad formulation. For example, this is not unique tetrad, but if you define the tetrad frame, something like this. This is a spatial metric anyway. And then so you can project any physical quantity like a conserved quantities and a vector, scalar you don't have to, but the vectors and tensor to the tetrad frame by using this tetrad basis. And because if you move on, if you transform to the tetrad formulation, this system is nothing but the special relativistic locally. So you can use you can solve the Riemann problem in a locally Minkowski spacetime, which means that you can directly use the Riemann solver invented in the special relativistic case. Then so you get the numerical flux in a locally Minkowski spacetime, and also conserved quantities in a locally Minkowski spacetimes. By transforming back to the inertial frame by again this tetrad basis, then so finally you get the numerical flux in the curved spacetimes. So no matter what you employed in the Riemann solver in the Minkowski spacetimes, this tetrad formulation gives you the naturally taking into account the curved spacetime information through the tetrad formulations. So for relativistic hydrodynamics or relativistic magnetohydrodynamics, the most simple or robust but a little bit less accurate scheme is a HLL type scheme. I think I have already introduced this scheme in non-relativistic case. And the concept is exactly the same in a non-relativistic case. For HLL, you consider that this time diagram, space-time diagram, for the left propagating wave and right propagating wave. But the point in here is this space-time diagram X and T is not the inertial frame, but the local Minkowski space-time. So this space diagram should, this scheme should be applied after the tetrahedral transformation. So in HLL, so you don't take into account the internal structure inside the Riemann form. So if the left propagating wave is the this direction, for example, in this diagram, and the numerical flux is given by the left state of the physical flux, and in the middle, the HL state, in the right, in the light state, in this case, the light state of the physical flux. But in curved spacetime, and this orthogonality is guaranteed in the tetrahedral frame, but it doesn't mean that the interface, initial interface, stays along this line. Because of so, if you calculate dx by using this tetrahedral and the trajectory of the cell interface, so you may have this red line, which describes the interface is constant in inertial plane, but not in the tetrahedral frame. And this the interface drag interface velocity is proportional to the shift vector dx. This is a consequence for the frame dragging effect. So the HL solver in curved spacetime case, so we need to evaluate, we need to take into account this shift vector information in the numerical flux. For example, in this example, if the lambda L left propagating wave is greater than Bx, in this case, okay. In the first case, lambda L is something like this, but here is the x j plus 1 over 2 is a constant, which means that beta x is proportional to the shift vector, right? If that drag velocity is smaller than, sorry, no, I'm wrong. Here, x in special relativistic case, if this Riemann form structure something like this, the next solution, the time steps, the solution at next time is given by this, right? So you can say that, oh, here is a left state. So you can evaluate the numerical flux as a left state of the physical flux. But in this case, if the dragging effect is something like this, so you need to take it, because you need to take into account here, because here is a next time step for at the interface, right? So in this case, the physical quantity left numerical flux is given by the physical quantity in the left case. And the center, if the case is a schematic picture for like this, if you have HL and HL, lambda L and lambda R, and if you drag something like this, and the next solution is given by these equations. Also, the other case is if the drag interface drag velocity is greater than lambda R, if this red curve becomes something like this, it should be the light state. Okay. So also this is this numerical flux naturally take into account the frame dragging effect or general relativistic information. And HLL, the state is given by this by this formula, as I derived yesterday. So now, okay, this is a completion for the HL scheme for relativistic hydrodynamics and magnetohydrodynamics. But this is a standard technique in numerical relativity community, but the other community, it is known, this is very diffusive or very less accurate because this scheme completely ignores the internal structure of the Riemann fan. As we have learned from Mondays, we know that in relativistic or non-relativistic hydrodynamics case, we have a three kind of the waves, right? One is a left propagating wave, and one is a right propagating wave, and the final one is a contact discontinuity in the middle, right? So in HLC type scheme for relative, or this is only for relative hydrodynamics, you take into account or you restore the internal structures coming from the contact discontinuity, something like this. So now you have a four state, L state, and the CL state between the left propagating and the contact discontinuities, and the CR state between the contact discontinuities and the light propagating wave. So then, if this condition is satisfied, which means that the Riemann fan is something like this, numerical flux should be given by the left, the state of physical flux. Also, if this condition is satisfied, which means that the lambda c becomes something like this, and then the physical state should be given by the CL state, right? And the third option is written in these schematic pictures because this is a constant trajectory of the interface. In this case, the numerical flux it should be given the CR state, right? Do you understand the meaning of this figure? Okay. In special relativistic case, if the wave structure is given something like this, so now you say that, okay, next step is a CL state. So we should evaluate the numerical flux as a CL state. But in general relativistic case, if the internal interface velocity is something like this, the next step should be given as a CR state, right? So this is the schematic picture of this. So the final option is if the light propagating the wave is smaller than interface velocity, the final state should be given by the R state of physical flux. Okay. Then the next task is to relate this CL state flux and the CR state. How to do that? So we know that the Rankine-Hughes relation gives you the relation when you are close the waves, right? So CL state, for example, is given by the left state physical flux plus the propagation of the speed of the lambda L times difference between the CL and L and the CL state of the conserved quantity. This is nothing but the Rankine-Hughes relations. For the CL state, the thing is similar. You connect from the light state by jump close to this light propagating wave, then you can finally get this expression. So the final task is to get the conserved quantities in the CL and CR state. So how to do that? So because at the contact discontinuities, the X component of the three velocities should be continuous. This is properties for the contact discontinuity. And we don't know that the internal, the pressure of the internal structures. So we have to solve this equation in terms of the unknown intermediate state pressure PC, which is a constant inside a palm. And by using a Rankine-Hughes relation somehow, so we can estimate the contact discontinuity, the characteristic speed lambda c by these equations, where the coefficient something HL is the HL state flux and HL state conserved quantities. Then you can analytically solve this equation in terms of the lambda c. And lambda c, then you get the contact discontinuity characteristic speed. With these quantities, the unknown, the intermediate pressure is given by these equations. So now you know that the contact, pressure, intermediate pressure inside a Riemann form. Okay, now so you can calculate the CL and CL state, conserved quantity in the CL and CL state. This is again the Rankine-Hugoni relation. Now you know the lambda c. Also the flux is given by these equations, and you know the lambda c and the PC, and L on the right state is of course known quantities, and also the energy densities by this relation. This is Rankine-Hugoni relation as well. So you know the PC and the lambda c, you can get these physical quantities. So now, so you solve the Riemann problem. You know the lambda L, lambda C, and lambda R, and you already know these quantities. And you also calculate the conserved quantity in the CL and CL state. Then, so by using the Rankine-Hugoni relation, you know that the CL state flux. Then, so by considering these conditions, now you can get the numerical flux at the cell interface. This is the relativistic hydrodynamics case. So this is a more advanced one for relativistic magnetohydrodynamics case. The HL in magnetohydrodynamics case, I didn't explain at all, but in MHD case in general, the 7 waves appears. For relativistic case, you have 3 kind of waves, but for MHD case, the 7 wave appears. This is a fast wave, left propagating fast wave, right propagating fast wave, and left and right propagating slow waves. Left and right propagating alpha wave, and left and right propagating slow waves, and contact discontinuity, in total 6. But in HL scheme or HLE scheme, which is standard in our communities, completely ignore the internal structure of the such a the internal structure inside the Riemann file, even for the magnetohydrodynamics, which means that you may lose some important information and you get a super diffusive result. So HLD is the more advanced one, in which the 5 of 7 waves will be considered, which means that you take into account of first wave, left and right propagating, and left and right propagating alpha wave, and contact discontinuity, but you ignore the slow waves. So the things is very similar for the HLC case. If you take into account the frame tracking effect, there are the 5 cases for the numerical flux, which means the left state case, or left of the alpha wave case, or the between left states between the alpha wave and the contact discontinuities, and right state between the contact discontinuities and alpha wave, and the right state between the light propagating alpha wave and light propagating fast wave, and the final is a light state, right? You have a 5, there are 5 cases. Again, so the physical flux of AL state or AR state or CL and CL state is given by Rankine-Hugoni relation. For example, for AL or AL states, you start from the left and right and jump across the first left propagating wave or right propagating wave. Then so you can get the physical flux of the AL and AL state. And for CL and CL state, you jump from AL and AL. You jump from the AL and AL for across the alpha wave. So then we finally get the flux at the CL and CL state. The final task is to obtain the lambda AL and lambda AL, also conservative quantity in AL and AL state, and CL and CL state. This is a task for the HLD type. But I have to mention about the wave speed in these programs. So basically, you have 7 waves, but we ignore the slow wave, 2 of 7. So there appears 5 waves. 2 of them is fast waves The characteristic speed is approximately given by these equations. This is given by the diagonalization for the Jacobian matrix in a special relativistic MHD case. And also the Alfvén waves given by these equations, and finally contact discontinuities in the middle here, right? So let's calculate the coupled state. So we start from the left and right state. This is a known state. Let's define R something blah 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 by this quantity. F is a physical quantity, and the lambda is the wave propagation speed. Right-hand side quantities are known quantities given an initial condition. You know that these quantities, right? And in this, okay, sorry, this is just a x direction problem. So in this problem, dx should be constant because of divergence-free condition. So given the initial guess of unknown intermediate total pressure, P total in the inside the Riemann fan is constant but unknown. So we can derive the 3 velocities at the AL and AR state with this messy expression. But the point is, in right-hand side quantity is known except for the P total. For example, P total is contained in here, but the other terms are known, from the left and right state. So by giving the guess or initial guess for the P total, you can guess the 3 velocity at the AL and AR state. With these 3 velocity, now so you can calculate the magnetic field in AL and AR state by these equations. And I won't derive this equation because it's super easy, but if you're interested in, please look at the original paper anyway. So also the total specific entropy is in AL and AL state is given by this equation, right? Everything is, okay, given the initial guess of the P total, everything is known. Okay. So now the conserved quantity in AL and AR state is derived from Rankine-Hughes relation and given like this, right? So now, we connected the solution from L and R state to the AL and AR state. Next is the solution. Next task is to connect the solution from AL and AR state to the CL and CR state. To do that, so let's define the sigma mu, which is defined by the ether for velocity and the magnetic field measured in a fluid rest frame. And ether is given by this equation, and the plus and the minus signs are left propagating and right propagating wave case, left and the right propagating case anyway. So if you define the upper K by using this sigma 1, and this expression is reduced this one, but you can realize Kx is nothing but the Alfvén speed in x directions. By examining the jump condition, you may come up with eta here and ki in here, and the total specific entropy do not change across the Alfvén wave. This is a property for the Alfvén wave. So now, you connect the solution from AL and R state to the CL and CR state by this equation, because the ether KIH doesn't change across this Alfvén wave. So then, you can write down for the known quantities given the initial guess for the total pressures. The final task is to connect the CL and CR state, right? And the magnetic field in the CL and CR state is given by this equation. This is again coming from the Rankine-Hughes relations. And finally, you have 3 velocity expression in CL and CR state here, CR and CR state. Because at the contact interface, the X component or normal component of the 3 velocity should be continuous. From these equations, BXCL and BXCL should be equal, right? And this gives you the this expression by plugging this one, and y and blah 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 is a known quantities. And this equation gives some improved guess for the next iteration for the p total, because p total is a known quantities. Let me repeat again. So we start from the unknown quantity initial guess of p total. We know that we can guess the AL and AL state. Also, we can guess the CL and CL state. Then, so you can connect the 3 velocity in CL state and 3 velocity in CL states. And then, so this, because of this condition should be satisfied, you can improve the, finally you get the improved guess for the p total. Then, so we go back to the first procedure is here, right? Because the p total is updated, then so you repeat that procedure until that you get the convergence. And this is a HLD solver. And also, okay, the conserved quantity and the CL and the CL state is given by these equations finally. And now, so you have a solution inside the Riemann pan. And depending on the how first these waves and how first the interface is dragged, you can estimate the numerical flux at the interface. This is a HLD solver. And as far as I know, this is the best approach in numerical relativity hydrodynamics by performing the standard test bets, this solver is much accurate and less diffusive compared to the HL solver, which is standard in numerical relativity communities. Okay, this is a low scheme, but okay, so I won't jump into the detail of the low scheme, but there is a low scheme in relativistic hydrodynamics versions. And but the tricky point is relativistic the low time scheme. You need a decomposed Jacobian matrix. You need to diagonalize a Jacobian matrix to get the upper lambda and right eigenvectors and the left eigenvector, as we learned in the 2 days ago, the lectures. But in general relativity case, this decomposition becomes super meshy. In particular, in general case is not the gamma rho or polytropic equation of state case, but the tabulated equation of this case. It is almost impossible to do our decomposition. So this low scheme was employed, let's say, 15 years ago in numerical relativity communities for relativistic hydrodynamics, because at that time, the people stick to the very simplified setup like a gamma rho equation of state or polytropic equation of state. But nowadays, everybody or many people include neutrino radiation transfer or magnetohydrodynamics. In this case, the numerical relativity communities doesn't implement a low type scheme anymore. So now is the time for lunch. The exercise for today or tomorrow is generate a relativistic Riemann solver from scratch for the relativistic hydrodynamics. Relative MHD case is too much, so I would say please generate or please write a code from scratch relativistic Riemann solver in hydrodynamics case and compare the exact solution. You may or you will write a core Python script from yesterday exercise. Okay, this is the lecture of today. If you have questions, or if you don't, let's go to lunch. Okay.